Hey everyone, welcome back to HS Tech Channel. This is going to be a start of a tutorial series that's going to show you, if you're a completely new user of mainframes and you're running ZOS, more or less how to use ZOS. Now, I will say that I have produced a series of videos in the past on the exact same subject, but looking at those nowadays, I've noticed that there's a lot of factual errors in them, and so these videos are going to be more or less a correction, if you will, to those, but also a more demonstrative approach from a more academic standpoint. So, if you are a new user who has never used ZOS before, you may wonder, why in the world am I using Windows NT? Like, what has this got to do with ZOS? Well, we're just running an old program called PCOM. Now, this program is still used today, and if you're at a mainframe shop, you may find that you actually still have personal communications, or again, as we call it, PCOM, available to you. Let me explain why we need this. If you are used to the standard world of Unix style operating systems, you're familiar with the concept of like Xterm and VT100 style terminals. We don't really use those on mainframes. Well, we do, but not for hardly anything useful. Instead, we use terminals called 3270 terminals, and these are radically different, and they require a lot more effort to use and emulate, and there are a variety of terminal emulators out there that you can use. PCOM, Vista TN3270, ZOC, PW3270, and of course the legendary X3270. But this right here is IBM's own terminal emulator, and I'm going to show you how to use this here. So when you start it up, you're going to be given this menu kind here, although nowadays this would say Z series rather than S390. You can tell what year this is from. This version is from 1997. And then I go ahead and punch in the IP address of my mainframe, which will be this. And if you want, you can enable graphics, set your code page. If you're not in the United States, you will need to set a code page. And if you want to program in C, well, I'll have a dedicated video on that. Programming in C is notoriously difficult because you can't really type brackets on here, but don't worry, I'll show you how to do that. So go ahead, do that, and I'm going to warn you, the 3270 key map is very different from what you're used to, because if I press enter, it's not actually submitting anything, it's just taking me down. So you'll want to hit the map button, which still exists today, and if you already have a prepared key map, you can open it. But you'll want to bind this key here to enter rather than new line, this to clear, so escape is clear, and then you're going to want to have some kind of PA1 and PA2 and PA3 key. Now, normally, that is, you can see right here, Alt Insert. In case you're wondering what clear is on its own, it's just pause break. This control right here is the default right enter, but in this case I have Control 1, Control 2, and Control 3 set to the PA keys, alright? So say yes to that, and I think if we're able to maximize, we can get a little bit more screen real estate here. So this is the logon screen. This is a ZOS 1.5 system, so it's rather old. It's actually going on about 20 years old, but the beauty is that nothing has really changed. Well, the basics haven't changed. I mean, the specifics have certainly changed, but the gist of it will be the same even today. This is running on my System 390 that I have in my bedroom. Yes, really, I have a mainframe in my bedroom. If you've never watched my videos before, that'll be the least unsurprising thing. Alright, let's go ahead and log in. So go ahead and, if you know your username, go ahead and punch in your username, but we'll do it the manual way. So we'll do LTSO, and hold on, I gotta explain what this even means. There are a variety of subsystems, if you will, that this ZOS machine that I have is running. What we wanted is, we want to log into TSO so we can actually do something useful with the operating system. CICS is a transaction processing environment, which I will make tutorials on. And IMS is a combination database and transaction processing environment. If you want a bit of tidbit of computing history, IMS was basically the first real database. Alright, so we'll log in as TSO. Now, If you already have a username, great. If you don't have a username, or you're running your own ZOS, you'll want to log in as IBM user with the password sys1. But in this case, I have a real account on here, so I'll log in as me. The logon procedure, if you want to change your password, stick it in here. The logon procedure, there's several of these, and they're dependent on the site. The system that I'm running here is obviously a development image that IBM puts out, and it comes on a stack of like 20 CDs. You feed the CDs into your mainframe, and you dump the disk files to the drive array, and you're off to the races. So the logon procedure that I'm using here may not exist on your system. You may be using something like DBS Proc 8 or even DBS Proc 9 or ISPF Proc or ISPF Lite or OMVS Proc. You have a variety of procedures at your disposal here, but I'm just going to use that one, so I'll go ahead and log on, and it takes a second. This is rather slow. It is a rather old machine, and it's running as a virtual machine on a mainframe, but looks like we're in. Now, whenever you see the 3 stars, that's an invitation to either press enter or press clear. So remember, enter is just a normal enter key, and clear I change to escape. In this case, we'll hit enter, and we'll see the main menu of essentially our panel-driven user interface. I have no idea why this machine is so slow. There we go. That only took 12 years to open. So hit enter to dismiss the welcome message, and this is what you got. So ISPF is one of the most critical programs that you will be using, along with another program called SDSF, which we will be looking at. And this is basically your combined editor and dialog manager for your mainframe. Don't worry about what it stands for in case you're wondering, it's like the Interactive System Productivity Facility or something like that. But really what it is your keys to the kingdom, so to speak. So, great. What in the world are we doing here? Well, we have a settings menu. We have a file viewer, except we call it a dataset on a mainframe. We don't call it a file, we call it a dataset, and you'll see what I mean by that. We have utility functions for datasets. We have compilers that we can invoke in the foreground, in other words, run them on our terminal, or we can generate a batch job and run a batch job in the background for a compiler. We can enter TSO commands, which are basically the mainframe command line environment that we're using here. We can test custom-made dialogues, because you can make your own dialogues like these. IBM Program Development Products, this is something you'll see on like every ISPF menu ever. SELM, Software Configuration Library Manager, don't worry about that, and don't worry about the Object Action Workplace. M is an interesting menu, because if we go into it, there's tons and tons of stuff we can run. Now, your site may have a different looking main menu. This is just a flat IBM default that they give you with the development image. If you're at like a real place that has like loads and loads and loads of third-party products, there may be a menu for third-party products, but in this case, this is just first-party software, because this is just the image that IBM hands out to everyone. So here's some of the stuff we can run. We are particularly interested in this one here called SDSF. Another useful tool is Ditto. You may need to use dfsort. OMVS enters a Unix environment, which we will be looking at. DB2 is a database environment, IPCS is a debugger, HCD, and HCD, ISMF, and SMPE. Unless you're a systems programmer, don't worry about those. And that is pretty much everything we need. And the performance expert is the DB2 performance expert. It's not like a system-wide thing, it's just for DB2. Okay, so how do we list files? What does a file even look like on here? Well, if we go to utilities, we'll have a variety of options for things that we can do with what we would consider our files, which of course datasets. So let us list datasets. Now, you got to understand the syntax of file names on this very strange operating system here. The file names look something like this. Okay, so it's qualifier.qualifier.qualifier, and if this dataset is something called a partitioned dataset, we can then have a member that looks like that. Now, if you ever need to specify a dataset name, if your user ID is WEC, wec.like.this can actually just be typed like this. But if you want to access this full dataset name in just a generic context, put it in quotes. Get in the habit of putting dataset names in single quotes. It will save you from so many dataset not found headaches, believe me. So, what we can do here is we can actually search for datasets. So let's look for everything that starts with my username. So in other words, datasets that my username owns. Here they are. So we have quite a number of datasets here. Some of these are source libraries. Some of these are online books. Just an interesting tidbit there. There's like a pre-PDF online document processing environment that ZOS has. And then over here is the disk that the dataset is on. So in this case, Z5 User 1 is the name of my my disk drive that has pretty much all my user files on it. OS39M1 is like the first important disk in the system, and temporary / automatically allocated datasets show up on there. So let's say we want to write a program. I mean, obviously we want to start with everyone's favorite mainframe language. We want to write a COBOL program. So how in the world are we going to do that? Well, first I'm going to observe this, see that there is data sets in there, but don't worry about that. Go back to your main menu and you can go 3 and 2, and we're going to allocate a data set, and we're going to allocate this data set here. So, okay, this is going to break into wec.source.cntl. Well, we don't want that. We want COBOL 2, because remember, I already have a COBOL data set that has other examples in it. I want to do COBOL 2, okay? So hit A to allocate. You saw that down at the bottom. And here's how you do this. Specify a volume serial. If you just leave this blank, it's going to throw you on some random disk, and who knows where it's going to end up, but don't worry, you'll be able to find it. It's not like you're going to lose a data set, but if you want, put all your data sets on the same volume. Maybe your system programmer wants you to do that. Maybe they don't. It's up to you. Space units. This right here is how many of whatever is here gets allocated. Okay, so I don't need 280 megabytes of COBOL source. So I'm going to do KB, and I might have a 5 kilobyte COBOL program maximum. The primary quantity and the secondary quantity is basically, the primary quantity is what you're given now. The secondary quantity is when you run out of space in the primary quantity and you need more room, okay? So it's basically a room to grow. Directory blocks. This is important if you have a partition data set, okay? If you have a sequential data set, that's just, there's no parenthesis, right? So there's no members, it's not a source library, it's just a plain flat file. But if you start adding directory blocks, now you have something called a partition data set. And that has multiple members, and it's more or less what you store your source code in. So we're going to cover both of these. So we're going to make a PDS, partition data set, for our source code. And then we're also going to make a sequential data set for just a demonstration purpose. The record length for COBOL programs needs to be 80, and it needs to be of the FB record format. Now, if you're in Unix, you probably already know how in the world files work. You just write data to the file. That's pretty much it. You don't have to specify any record formatting parameters. You don't have to know the block size. You don't know any of this stuff. It's just a bag of bytes. This is not the case on a mainframe. It's way more sophisticated. There's a reason for this, but what you need to know is that if you're writing a source code for a program, you want to do a FB for a fixed block with a record length of 80. What that means is that the files can have a maximum of 80 columns in that, okay? If you change it to 132, then that's what you get. Then come down here, remove anything from the block size, and hit enter. Okay, so the data set was allocated, ignore this, that's fine. And then with nothing in the option field, hit enter and you'll see the results. Okay, so it computed a block size. Again, don't worry too much about the block size. And we should be good to go. So now, go back to your main menu, go to your editor, punch in this right here, and now we need to specify a member name, okay? Remember, this is not a flat file, so we won't be able to edit it because there's no members in the data set. But if you just hit enter here, and there are members in the data set, it will show you a list, and you can come down and tab down and hit S in order to select one, okay? So we want to do cob high, all right? And now we have to figure out how to use the editor. So warning, the undo command is not available. That's fine. Type reset. And now you see I'm tabbing around, come here to these red stars, hit I, and now you can start typing your program. Okay, push enter twice to stop auto-adding lines. If you want to add lots of lines, do like I and then the number of lines you want to add, and then, put some garbage in. To delete a line, come over here, put D in there and hit enter. To delete a range of lines, do DD like that, and you can copy like that, and then you can do A for after, or B for before, okay? You got that? If you want to copy a range of lines, you can do CC and CC, and then you can do A to plop that in, and then we'll delete that. So that's a brief overview of how to use the ISPF editor. This editor is very sophisticated, it's very complicated, there's a lot of stuff you can do with it. There's a lot of headaches you can run into it as well, so just be mindful of that. So you saw me type save there, and we need to go back, so hit F3. In case you didn't know that's what I was hitting, you can see down here it says F3, okay? Now, let's go foreground, COBOL, and remember COBOL 2, and if you forgot the name of the file, you can hit enter, and it's gonna say, oh, there you go, and then come over here, hit S, press enter, so it's gonna load the file, and then after this, we will have compiled it. So, compiler's running, slow as Christmas, of course, because this machine is slow as mud and is probably hogged up running a Linux machine right now as well. And that's it. So there you go. We have successfully compiled us a program. But what is it good for though? Well, keep scrolling, you'll see everything looks good, no statements flagged. If there's an error, you'd see an error. Press F3 to go back. And then from here, on the option, hit D, unless you need this listing data set, which I doubt that you need. Okay? Push F3 to go back to the main menu, and do 3 and 4, and we gotta find where it saved its output. Now, remember how compilers work. You start with the compiler, so you compile, then you have an object file, then you link, then you run. Okay, so that's what we're gonna do here. So go look for your WEC, well, it would be your user ID. This is just my user ID. And look for all the datasets that start with your user ID. Sorry, that sounded really weird. Sorry, I had to clear my throat there. And look for wec.source.obj. Now, if you don't already have this dataset, it will be automatically created for you, but it might run out of space quickly. So if you want to make your own object dataset, which the foreground compilers will always deposit these into your user ID.source.obj, it needs to be fixed with a record length of 80, and it needs to be a PO, in other words, a PDS, as opposed to PS, which means physical sequential, as opposed to PO, which is physical ordered, meaning a PDS. And in this case, there are directory blocks to it, so yeah, this is basically just a PDS. So do the exact same thing that we did for creating the wec.source.cobalt2 dataset, and just reuse that for creating this right here. So we have that. Now we're gonna back up. Gonna go back up to the main menu, go to foreground, go to the binder/link editor. Now, what's the difference between the two? Basically just the version of ZOS that you're running. Nowadays it's all the binder, but many years ago you had the original link editor, but don't worry about that. Everything will just work for you. Okay, so punch in the name of your program, cob high, and inevitably you want to use the binder. You can use the linkage editor if you want, but it really won't work. Now, scroll down, F7, F8, you see backward and forward here. Okay, you need to specify this here. You need cee.sce linked. This right here is the Essentially, it's equivalent of like libc.a. Dynamic linking on ZOS is basically mandatory. So these right here are static linking routines, and then later you will specify a load library when you run the program, but you really won't need to do that. And then any additional libraries that you want, go in here. Syslib, note that this one's different. This one's syslin. This right here is if you want to load more object files. This one right here is for DB2 7.10, or I guess 7.1.0. And this right here contains the object modules for DB2. So you don't really need that, but I'm leaving it here anyways. So go ahead and hit enter. And then the link editor is going to run. All right. Processing complete, return code 0. That means that there's no issue. Scroll down, everything looks good. Save module attributes. The save module being the program that we have just successfully linked to run. Looks good to me. Now, at this point, we have two ways we can run it. Just go ahead and delete that. We can choose to run it from the terminal, or we can choose to run it from the file list, if you will. Instead, we're going to do it the cool way. So what we need to do here is we need to run a command, which you can already see in my history, that will allocate the DD name of sysprint to our terminal. Now, this is where ZOS gets even weirder from other operating systems. If you're writing a C program on Unix and you want to access a data file, you just fopen the file name. You don't really do that on ZOS. Instead, you open a logical name, okay? You open a symbolic name called a DD name. DD doesn't really stand for anything, it's just, you'll see what it means in a minute when we get to writing batch jobs, but you're allocating sysprint, that DD name, and you're applying it to star, which means your terminal, okay? So whenever the program opens sysprint and starts writing data, it's going to show up on your screen. So you need to do that. Now, if you want to run like a system-wide program, and it's a program that you know is accessible anytime, in other words, it's in the LPA, or the linked list. If you do call star and then in parentheses you have the program name, for instance, if we run this, it's going to flip out because we don't have sysin declared. See, there you go, it crashed. If we allocate sysin, and then we run this mysterious ICKDSF program again, more issues. But that's fine. I think you get the point. That's what a crash looks like. Now, let's run our program. So we do call, and remember in quotes, wec.source.load, and we're going to go look at that data set in a second because the attributes of it are completely different. Cob high, and it will run and it will show us exactly what we want, okay? So let's look at those data set attributes. This is going to be a bit weird. We have a record format of undefined. In other words, there is no record format, and a record length of 0, and then the maximum biggest block size that we can get. Now, this right here is basically the maximum length around one of the tracks on the disks. Don't worry about that. All you need to know is that when you're allocating a load library dataset, it needs to be PO, so physical order, so a PDS, see, there you go. There's our directory blocks. Record format U, record length 0, and then the block size is really all that matters. So you'll just specify 27260, and that's a good block size for a 3390 disk, which is, I guarantee, what you're using. So we should be good there. And now we can up the ante a little bit and get into doing batch jobs. Now, allocate another data set for your batch jobs. So, oh, wrong option. We'll allocate us I forgot the A. We want FB, we'll do 20. Remember, take that off. Okay, allocate us a data set. We're going to edit. And as you can see, it's blank. And let us make a batch job. Now, this is where everyone freaks out and all hell breaks loose. Everyone's like, oh, JCL is so hard. Well, you know what? In order to understand it, you need examples, all right? So let us start typing. So here's how you do a ZOS batch job. First thing you need to do is specify your username. Okay? And then you need some kind of characters that follow it. You get 8 letters, so how about WECC for our COBOL program? And then you do job 1, comma, class equal, oops. Class equals, I can't type there? What in the world does this think it's doing? Something has gone direly wrong here. I think I messed up my data set. Wow, if only. Right, yeah, you see what I did here? I specified an invalid record length. So what we're going to do is we're going to delete this data set, and then we're going to reallocate it, except this time we'll use our brain. There you go. Looks good. Alright. Now let's actually try that. Alright, the message class is basically where the output goes. Class A is usually a printer. Class H sends it to a queue where we can read it later. Class X also stores it in a queue, but it's intended to be held and then spat out on a printer later. So I always use class H because that's pretty much what everyone uses. And then message level equals 1, 1. Show us every error message it can possibly show us. Don't worry, the output is not that bad and not that hard to read. And now we gotta run something. So the way this works is you're basically running sequential step after step after step. So step 1, execute, and depending on how you have what follows this, it'll either execute a procedure, which is basically like a canned JCL sequence, or it'll execute a program. So we want to run program equals cob high, and now we need to tell it where to find the program. If you're running a program that is already in the system-wide linked list, ZOS will automatically find it. You don't have to tell it where it is, but in this case we have to tell it where we can find our program. So remember those DD names. We're going to specify DD names so we can do stuff here. So steplib is the library that has our program for this step, okay? DD, DSN for the dataset name is wec.source.load, comma, we don't specify anything in parentheses because this gets thrown on the end. And then we need a disposition here. So the way that this works is if you do something like new, comma, catalog, comma, delete, this right here will create a new data set. And then if that step completes normally, we're going to catalog it so it can be found. But if something goes wrong, we'll delete it. Alternatively, you can do old, comma, delete, comma, delete. If you want to read a data set, then delete it, and then if something goes wrong, deletes it. If you want to keep it, do pass. So in other words, don't do anything in that operation. But you can also just make it simple, and you can do share, which basically means don't delete it when you're done, don't create anything new, just read it. If you write it, great. It means shared access. It's basically the easiest way to access a data set like that. Okay, now we need to allocate an output stream for our text to show up on, okay? So that was sysprint DD, rather than a dataset name, though we can absolutely put a dataset name, and we will go back and do that. We're gonna say sysout equals star, and the star means it's gonna show up in the sysout batch log along with the program here, okay? And if you have a program that might accept input from sysin, but only under certain circumstances, we can do sysin dd dummy for no file at all, okay? Push enter, come down here, we're gonna do a save, and now we're gonna do a submit. Now, actually, one last thing before we do that, if you, on the end, you put notify equals your username, when we submit this job, we'll be warned of its success or failure. Okay, job submitted, and in just a second, we should get the bounce back telling us if it ran or not, okay? So there we go. It ended on our machine name, and the condition code is 0. Now, just like Unix, condition code of 0 indicates success, okay? Now go back to your main menu, and now we need to run STSF. Now, if you don't want to hunt it in the menu, because maybe your site has a different menu, just type TSO STSF, but we'll run it from the menu since it's, I think, easier. Go to M, and then 5, see, STSF. Give a second to open. All right, and from here, we can go retrieve our job output. So go to H, and here it is. See, it created it creates 2 entries in that, and I accidentally just completely backed out of it. In case you're wondering what I hit, I accidentally hit return, which kicks you all the way back to start. Instead of doing the held output queue, we'll do ST, and then here's our job, do S. This is the full output, okay? From the held queue, it breaks however many outputs there are into several discrete chunks. This is just everything all at once, all right? So you can scroll left and right with F10 and F11. So here's our banner. So this is the start date, obviously. This is a user ID. This is the last time we ever accessed the system. In this case, we logged in interactively, but in this case, we're submitting a batch job. Here's our job start, okay? Ended, and then that's the end of that. All right, so there were 5 cards, in other words, lines in the input file. And we can scroll through here, and this is the job status. So step 1, this right here is the address of a disk drive, which if you go look is equivalent to the disk where my load modules are stored, Z5USR1. Steplib, JES2, in other words, this job scheduler program, this is the job scheduler JES2, is allocated sysprint, dummy for sysin, and then there's always an implicit sysout allocation, okay? And then this data set here became temporarily created during the duration of the job so that it could hold our sysprint output, and then when it's done, it spits it into the job queue and deletes the old data set, okay? And then we kept our load data set, obviously, and then you can see this is the volume serial, in other words, the disk name where this data set was, Z5 user 1, and then here is our sysout for this, this data set here is the jobs sysout, and then this right here is our programs sysout, all right? So we start, we stop, we used 0.2 seconds of CPU or 0.02 seconds of CPU time, and that's the end, and then right underneath it is where the output starts. Now, if you have a program that has loads and loads of output, come over here and hit the question mark, and you can see the output for all of the sub-steps, okay? So if you have multiple steps in your program, and you only want the sysout, here you go. There's that. If you only want to see the JCL listing, there you go. If you only want to see the system messages, there they are. If you only want to see the header, there you go. Just like that. So you can do it like that, or you can just do S to see all of it all at once. Now, let's up the ante a little bit and let's write to a file. So in that case, we're going to do 2 examples. We're going to create a file from JCL, and we're going to use an existing file. And we're going to go in backwards order because I think it's pretty simple. So we're going to go to 3 and then 2. We're going to allocate whatever you type in here overrides this, okay? So it's going to be wec.test.seek for sequential data set. We want 1 megabyte of space. We don't need any secondary space. We don't need any directory blocks. We want fixed blocked 80, and then remove this. And this is a sequential data set, okay? So if I come over here and I try to edit wec.source.seek, or yeah, sorry, it's wc.test.seek. When we edit it, there's no parenthesis on that, so we're not going to do anything though because we'll let the program do the talking for us. But come back here and we will edit our program. And sorry, this should have been sysout. So we have our sysout dataset here, except this time it's going to be wc.test.seek disp equals old, keep, keep. You can do that, or you can do share. We will save, and we will submit. Wait a while for it to run. Looks good. And we can come over here, and we can browse all of our files, and we can find that test file down here. And there it is, it wrote it to the file. You can go check the job log if you want, but it will really be interesting. It'll be pretty much the same stuff. Now, what if we want to delete that data set? Well, we can edit this here, and we can add step 2, exec program equals IEFBR14. Now this is basically a dummy program. It doesn't do anything. It's basically just for the sole purpose of allowing you to run job steps without actually running a program. And we can do sysut1. It can be anything you want. You can name this anything, it doesn't matter. dsn equals wc.source.seek. Actually, we're going to replace this with step 3 because before we delete it, sorry, it's test.seek disp. We're going to do something before we delete this. We're going to print it before we delete it. Disp is going to be old, delete. Now be into that. Step 2, exec program equals IEBGener. Sysprint dd sysout equals star. Sysout dd sysout equals star. Sysut1 is our input file, and sysut2 will be our output, okay? So IEBGener is basically the equivalent of the Unix dd command. So it will copy from sysut1 to sysut2. So we'll have our dataset name. Okay? And when we're all said and done, we'll delete it, and then we will add a step 0 to this job to allocate the dataset for us too. And let's hope that we don't have any errors. If we have some errors, we'll go troubleshoot them, and that will be, see, we had an error. So we need to go figure out what's going on here. All right, so we come over to SDSF. Uh-oh, sysnd statement missing. I know where that was. That was for IEBGener, right? See, we made it to, yeah. So unfortunately, we accidentally deleted our data set, so we'll go back and recreate it, because if I do a 3.4 and list the files, you'll see it ain't there anymore. So we'll do a 3.2 and we'll allocate it again. And then we will demonstrate allocating it from JCL. Select you. Alright. Notice how our line numbers are all goofy. Do a renum, and then a save, and you get consistent line numbers. Alright, we'll submit that. Alright, that worked perfectly. To quickly access SDSF, do m, semicolon 5, semicolon st, and it'll go straight to our job list. Alright, and here we go. So, alright, step 2, condition code, good. Step 3, and you can see I uncatalogued the data set and then deleted it. Alright, and our dataset utility will copy that sysut1 to our sysut2, which is our printer output, and there it is. And then the dataset is gone. And of course I can come over here and I can show sysprint, just says dataset utility generate, and then sysut2 is the output of us catting that file, basically. Now let's create the dataset from this. So this is a bit tricky to understand and wrap your head around, so I'm going to show you some examples here. It's really not all that hard. So just, oops. Stop selecting. I don't need you. Step 0, exec program equals ISPF 14, just like before. And our dataset name is going to be wc.test.seek. The disp is going to be new, comma catalog, comma delete, okay? So the first thing we do is create it. If that step works, good, catalog it so we can find it. Otherwise you have to go manually look at every single disk and try to find it. And delete if something goes wrong. Come down here. We'll go over here and just line it up like that. Unit equals some kind of unit type. So disk, tape, who cares? In this case, it'll be sysda or sysdisks. Vol equals ser equals the disk you want to put it on. Z5 user 1. If you leave this blank, the system will automatically find space and allocate it for you. But speaking of space, we also need to specify how big the file is going to be. Space equals, now there's two kinds of syntax here. You can specify a record unit and then a primary and a secondary, or you can specify the record size, block 7, or block size, and then the number of records. That sucks though, so instead we're going to do, we'll be old school, allocate by tracks. We want we'll do 1 track primary and 1 track secondary in case we run out of space. Alright, so track is basically, just look up a hard drive diagram, see what I mean. There's no tracks anymore because the odds of your disks actually being SSDs, at least nowadays on mainframes, is pretty high, but you know, it's just an old school thing. And then we need to specify the file parameters. So DCB equals recfm equals rec, FB, LREC equals 80, and then the block size equals 0. This will let the system figure out an ideal block size for us. Alright, so we'll go ahead and do this. We'll do a renum, we'll do a save, and we'll do a submit. And we'll see if we get any errors. If something goes direly wrong, it'll be obvious. Alright, doesn't look like there were any errors. Now, of course, the file's gone. We deleted at that last step, but if you take that last step off, you can go and sit and browse it using ISPF's editor here. So, step 0. So, alright, so we cataloged our dataset, wc.test.seek, and it's on this disk. Alright, and then here's where we run our program and spit it out to our sysout file, which is, of course, this dataset. Alright, then this is the step where we print it, and then this is the step where we delete it. Down here, uncatalogued, deleted. So dataset utility generate, so it's just like before, except that dataset is now obliterated. Now, let's up the ante a little bit. Let's also make it so rather than doing a sequential dataset, we do a partition dataset. This is a little bit different, but it's not that far off. We'll allocate a PDS instead. Same new catalog delete thing, except this time, come over here, turn on insert. Some keys are stuck again. This PC emulator sucks. And then right here you have your directory blocks, so we'll do, I don't know, 5. Should be good enough. Set the DCB to the exact same thing, and one last parameter to add. DSN type equals PDS. Now there's other ways to specify this, but generally I think that's the best way to put it. So now we're going to output this to wc.test.pds and do insert member 1, and we're not going to delete it because might as well. I think you've seen enough of deleting datasets here. So we're just gonna get rid of that. Alright? Check your work before you submit it, because everyone knows how slow this machine is. Alright, we'll submit that. Okay. Alright. Go over here. Go for your job status. Golly, this is so slow. Alright, there we go. Alright, looks good. Nope, sorry. Hands are off on the keyboard. And then here's our test PDS here. can browse a member in that, and if you want, you can delete the member. I won't do that. You can copy it to somewhere else, like there. Here's that member. Except we don't need it here, so we'll delete it, but there you go. So what else can we do on here? Well, for one, we can generate JCL to submit jobs in the background. Now I'm going to warn you, the batch selection panel, at least on flat cuts as EOS, tends to be questionable at best, but that's fine. We're going to do it anyways. So we're going to compile our CobHi program, and looks good to me. So the sysout class is going to be H. And so this generates a job step, okay? After this, we can link edit it because it just generates the next step. Don't forget this here. All right. Now, when we hit F3, it's going to generate the job. Enter job name characters. This is the stuff that follows your user ID, okay? So we do that. So it's grinding away in the background, and while this painfully slow machine, because the CPU is busy doing other important stuff, runs, there you go, we get our job output. Actually, there's two ways to view job output. You can actually come over here to outlist, and you can look for list all jobs with the TSO status command. You can also print a job and delete it from the held queue, or you can display job outputs. In this case, we're going to select WEC CMP, and if it finds it, great. If it doesn't find it, we'll have to use SDSF, but there you go, it found it. Just another way of viewing stuff. And you can see it automatically generates JCL, but boy, is it ugly. And you can see where it files the dataset after it's created, or it files the object right there. Okay. So that's the compile, and then here's the link. All right. It will delete the job from the queue. It's as easy as that, really. Now, inevitably, as you create more and more members, you're going to need to do something called compressing a data set. Now, this doesn't mean like gzip compression or like anything like that, but what it does is as you create members in a PDS and delete them, eventually you have to defrag the PDS. The technical term is ungassing or degassing, so we're going to degas our data set with that option there. So just defrag that there, it's as easy as that. And it's really not that bad. Now there's other useful utilities programs as well. Did you know that there's actually a client-server user interface that you can use? We can actually use that, but who cares? And there's versions of it for Windows, AIX, HPUX, OS2, and Solaris. It's actually a pretty cool trinket program, but I will demonstrate this later when I also demonstrate the CMS desktop program as well for VM. It's another interesting thing. In case you're wondering what manual is, it's in file. So you basically just download this member from this data set, and yep. Speaking of which, let me show you how to find important data sets on the system. Pretty much everything has some kind of prefix. So like isp.s, isp GUI, that's a data set that we can go find. And you can see there's the versions for various systems. But let's say we want to list all of ISPF's core data sets, we can just do that. And there they are. Now, other stuff has a prefix. So for example, the COBOL compiler is IGY. Put the star on the end, because you may have multiple versions of it installed, or you don't know what the version that follows it is. And so here is this data set here actually contains the COBOL compiler itself. There's a lot of stuff in here. I mean, I know where it is, but we can just do locate IGY CRCTL to find that member. This right here, if I call this, it will try to run a compiler. It's going to freak out because I don't have temporary files allocated, but this is the exact same thing as running the compiler. So it's running right now, except there's a program that it's trying to enter. To stop typing syslin on TSO, do this. So there you go, syslin statement missing, but there you go, the compiler technically ran. So that's that. If you want to run the PL1 compiler, it's this right here, IEL, and one of these is a compiler. Pretty simple. The C compiler is CBC. The Rex compiler is FAN. And the assembler is... Oops. Oh yeah, be very careful. Yeah, screen input error. If you ever clear your screen on ISPF, just bounce around a few menus to redraws. Just be careful with that. This is the assembler. And if I'm not mistaken... Yep, here you go. So, ASMA 90 is the assembler. We can just call that for fun. Yeah, syslib, sysin, I don't know, open the object file. Go figure. Those are errors directly from the assembler. Okay, that's the assembler itself. And there is also... There's also this here, which for some reason exists. This right here is an interesting program. This is a disassembler here. Oops. So it's asking for input here, but no member name found. We could disassemble something like IFBR14, which it couldn't find, but anyway, that's a disassembler if you need to do, oops, sorry, I hit the microphone with my hat. Alright, so that's the gist of that. That's how you find stuff. Now if you really want to find stuff, you can do **.cntl, and that will let you locate. See, so here's every dataset that has CNTL in the name, including mine, and there's others as well. So that's how you find stuff. You can initiate hard copy output. In other words, you can print and keep. So you can do something like wc.source.cobalt2 cobhi. This will do a batch print. If I do A, it'll come out on my actual printer, but if I do H, it will actually spool it. And then from here I can do F3 and do print. And all this does, if I go back to SCSF and look at the job output, you'll see it actually spits it out into the job queue. And it doesn't actually print it, it just generates a spooled output, really. And you can see it does the exact same thing that I did, which is IEB gener, and there it is. It prints just like that. Pretty simple stuff. Now, you can also display active users, but you're only really going to be able to see yourself. That's on purpose. A poorly configured ZOS system, you may be able to see everyone, so just be mindful of that. There's other useful things we can run on here, like Ditto is a wonderful file manager program. There is, of course, the file manager for ZOS, but we can browse data. We can browse a tape, a disk, VSAM files. Don't worry, I'll one day do a VSAM tutorial. Or I can just browse my virtual memory. So here's the virtual memory of my user session. You can also print data. You can copy data. Pretty useful. If you want to read a raw file or like a plain file or a flat file, do QSAM. Alright? And you can output that to whatever you want. This is useful for also processing tapes as well. So you can rewind a tape, or you can erase a tape and format a tape. Just keep that in mind. Ditto's a useful program if you have it. There's also the file manager for ZOS. So you can browse data. This is pretty much just like ISPF, really. There you go. So there's our file that we browsed. However, this is interesting because this can actually browse VSAM files as well. Well, kind of, if it would hurry up and show. You can specify a VSAM dataset and it will allow you to browse a VSAM file. Now, what is a VSAM file? It's basically like a built-in dataset for ZOS. It's a bit cumbersome to create VSAM files, but you can actually create them from here. So you can update, stuff like that. So we can create data. So we'll create a VSAM dataset just for fun. So how about wc.test.vsam? Volume serial Z5 user 1. Record length, we'll do 80. Records, number of records, 5. Fill character, rand. Key position, we'll start at the first column. Key length of 8 and increment the key by 10. Again, VSAM is a database, it's a key value database. Processing option looks good. Now this actually stuffs a file with data as well. So we want to do a KSDS file. So in other words, what it takes to create a new one. And you can create a non-VSAM dataset too, but I think we've seen enough of that already. All right. Uh-oh. Where do I need to enter? We'll do... I probably need to do this. Key length was 8. Actually, it will automatically enter that stuff for us. Let's see if it takes it. All right, 5 records written. There you go. And now we can browse that. There you go. So here's our key. And then the rest of this is the value. So it's just like we expected. Now, I will do a full tutorial on VSAM at some point, but that's just the gist of it. If you need to create or just browse VSAM files, you can sit here and you can use the ZOS file manager. You can also delete and actually, yeah, we'll do a print too, just to see that. Alright, and so it literally just spits it out on your terminal. That's always useful. And if we go back to our main menu, we can also dump something onto a tape. So we can copy tape data, possibly to and from a file. We can write tape marks, which is how you basically say end of file on tape. You can initialize the tape, erase the tape. Initialize writes the like the vol1 header. Erase, well, completely erases the tape. Summarize the tape contents. If this looks awfully similar to Ditto, it's because the programs are kind of related. But I'll exit from that, and I'll actually go to Ditto proper, and I can show you how to use that. So we can browse data. We can browse a VSAM object. There you go. Looks suspiciously familiar. Yeah, it's because it is. And when we're done, we can browse the file. It's going to look a little bit different because you see here it is. You note that the base dataset name is a VSAM file. Here's the data and here's the index. If you want to delete it, you can go over here and hit D. And this is what it takes to delete this. Yep, looks good. Execute. And she's gone. There it is. So hopefully that's a good introduction of how to use ISPF. There's other things we can do too, like we can go into this Unix environment. And this is interesting. There's an entire Unix subsystem on here too. And it's actually shockingly useful. So if I do uname-a, you'll see the operating system. It always claims OS 390. Here's the node ID. This is 1.5. And the CPU is a 7060, which is a Multiprice 3000. We start in /u/wec. We can look in the root directory. We can look under user. We can look in LPP and you can see everything that you have on here. So that's a lot of stuff. None of which I really know how to really use, not all of it, but there is stuff under here like a COBOL compiler. So COB2 is the COBOL compiler for Unix. There you go. So if you want to run the COBOL compiler from anywhere, we can do export path equals $path, and then we can add this into our path. And now I can run COB2 from anywhere, but we kind of need to get us a file going. And this is a line mode terminal, so we're not going to use VI like this. Instead, what we can do is we can open something called the I shell. This is really cool. If I look in these, you can see I have a shell history file and that's it. I can bring in a file to the Unix environment from the MVS environment. And really the easy way to do that is to do ocopy. So our input file is going to be wz.source.cob2 cobhi. Oh. Oh, it's a DD name. Oh, that's right. Well, press PA1 to stop the command there. Alloc F says UT1. This is gonna be sucky. Is it output? Yep. So we'll just do this instead. So our input dataset name is wc.source.cobol2 cobhi. Path name /u/wc/cobhi.cob. Up. What? Well, I guess I put it somewhere. Suppose we're about to find out. There it is. All right, so we will return to the shell, which we can access by typing omvs. I think it was export path equals $path user lpp cobol bin. Yep. There we go. Who would have guessed, right? All right, so we're compiling. There we go. Oh, now it's linking. And you can see fundamentally what this was is a combined compile, link, and go command here. So we can run cobhi. In fact, it will work. But there's the listing. Yep, looks good to me. And if I do a file on all this, you'll see that. Well, never mind. So much for that. But it does create object files. And yeah, so you can relink it if you want, but it's not super hard. Just be mindful though, it creates a mode 777 program. Yeah, I don't think that's the case nowadays, but just be mindful of that. That may be a security issue you have to deal with. But I think I'm going to go ahead and cut it here. I think this has gone on for long enough, but I hope that this was a good tutorial and hopefully provide you some good information on where you can get started. And if you have any future requests, let me know. But the next one I do is going to be on DB2 programming, and then after that it's going to be Kix programming, and after that it's going to be Kix and DB2 programming. Whew. It sure is a lot of work, ain't it? Alright, good luck everyone. Remember to get out of here, come over here, do 2, and log off. Just like that. Alright, everyone take care, have fun, and most importantly, good luck.